Today's video starts a unit on chemical bonding. There are two kinds of chemical bonding, probably familiar with this already. We're going to look at it a little more depth than we've seen before. There's ionic bonding, which will be today's topic, and then we're going to spend quite a bit of time on some nuances of covalent bonding. How ionic bonding works is a crystal is formed when oppositely charged ions minimize how much energy is stored in the attractions that they have for each other. So if we have an ion, like a sodium ion, for example, it's a 1+, and a chloride ion, it's a 1-, they're attracted to each other. And if they're held apart in space, there's energy stored in the fact that they're at distance from each other because there is this strong attraction pulling them together. Once they get close together, so the sodium is right next to the chlorine, well, there's no longer as much energy stored in their attractions, and nature hates these high energy situations, and so these crystals are naturally going to form. The crystals will be three-dimensional, and they'll be stacked together in the closest way that the two ions can be arranged. These elements are only going to bond ionically if the compound that you get when you're done is more stable than the individual elements were when they were far apart. Of course, that's typically the case for ions, but would the ions even bother to form? Well, we can look at this in terms of energetics because we know that energy is a state function. We can come at it in a couple of different directions. If we think about the process of sodium and chlorine, for example, becoming sodium chloride, there are a number of things that need to happen. The first thing that would have to happen is that the individual particles will have to become gas atoms. That's going to be an endothermic process. In this example, sodium becomes a gas when it vaporizes. So this reactant set changes to sodium gas and 1/2 chlorine vapor when sodium vaporizes. And delta H for that process is equal to 107.8 kilojoules. I put a plus sign here because this is an endothermic process. It takes energy to vaporize this solid sodium. The next thing that has to happen is the chlorine molecules have to be broken up. So that's the next step. You have to break up the bonds on diatomic molecules. So now we're going to Na gas plus a single Cl atom in the gaseous state. That's an endothermic process. It takes energy to break bonds. And so we have a positive 121.3 kilojoules to the system. And the next step is we're going to ionize the sodium. So the reactant set changes to sodium ion in the vapor state plus chlorine atoms, also as a gas. The delta H here for this process is equal to the ionization energy, actually. First ionization energy, which for sodium is 495.4 kilojoules. So now we've added energy in 3 separate steps, and we've gotten to the point where we have a sodium ion and a chlorine atom in the gaseous state. The next thing that's going to happen is we're going to ionize the chlorine by adding an electron. So we'll end up with sodium ions as a gas and chloride ions as a gas. This is an exothermic process. The electron affinity is actually the delta H here, and that turns out to be a minus 348.8 kilojoules. So the system loses energy in this exothermic process. And then the last step to becoming a solid sodium chloride crystal is these gaseous ions have to move together towards each other. And of course that's a release in energy because they're attracted to each other. Delta H for this process is what we call the lattice energy. And for these particular ions, that's minus 787.0 kilojoules for every mole. Now, if we go around this circle clockwise and add up all these steps, 107.8 kilojoules plus 121.3 plus 495.4 minus 348.8 minus 787.0 kilojoules, we end up with a negative 411.3 kilojoules. That's the difference between being here and being here when you go around this series of steps clockwise. But it's also the same difference as if you were to just go straight from starting point to ending point. And this happens to be the delta H of formation for sodium chloride. So the steps: separate the particles into individual gas atoms, vaporize solids or liquids to do that and break up any diatomic molecules. Then you have to ionize the cation, which will be endothermic. Then you have to ionize the anion, which will be exothermic, at least for the first ionization. And then you combine the ions to form a crystal, which would be exothermic. And that releases an amount of energy called the lattice energy. In practical terms, if we're going to try and quickly determine what's going on in ionic bonding, we can rely on something called the octet rule. The octet rule says that atoms tend to form ions that have the electron structure of the closest noble gas. Now, for most ions, this is going to mean they're going to have a full octet, or 8 electrons, in their outer shell, because most noble gases have a full 8 electrons. Because remember, they typically are going to end in P6 followed by an S2. And so in the highest energy level, that adds up to 8 electrons. There are some exceptions. One of them is elements for which helium is the closest noble gas. And that's because helium only requires a duet. It only requires 2 electrons to be stable. So remember, helium's notation is 1s2. So lithium would be an example. Lithium starts out as 1s2, 2s1, and when it becomes a lithium ion, an Li1+, it's just 1s2. That's stable. It's not a full octet. And transition and post-transition metals are also exceptions. Like, let's look at iron, for example. Iron is argon, this is the shorthand notation, 4s2, 3d6. It's going to lose its electrons when it ionizes from the highest shell, which is the 4s shell. So an Fe2+ is going to be argon, and then the 4s2 are gone, but the 3d6 are still there. And then Fe3+, which we also know is common, you're going to have to lose that third electron from the 3ds, and so it's argon with the 3d5. Neither one of those show a full octet. So transition metals and things that are closest to helium are exceptions to the octet rule. A handy device for keeping track of this stuff is Lewis symbols. They're invented by G.N. Lewis, who's shown here as a young man. He was an American chemist who actually gave a lot of insight into organic chemistry. One of his contributions to chemistry is this bookkeeping device for valence electrons called the Lewis symbol. So it's a valence shell bookkeeping device, really is what it is. The Lewis symbol uses dots to keep track of how many valence electrons are present in a given atom or ion. And this is the general format. You write down the symbol. So this is a generic symbol, X. And then put up to 8 valence electrons around it, depending on how many electrons are actually in the atom. So for a noble gas, there would be 8 dots. Here are where the 8 spots go. 2 on each side. Imagine a little square around this symbol. There are spots, 2 on a side, for 8 electrons. Here's an example. Oxygen. Let's do a Lewis symbol for oxygen. It's 1s2, 2s2, 2p4. Well, the valence electrons are the only ones that show up on the dot notation or the Lewis symbol. So 2 is the highest shell here. So that means we have 6 valence electrons. 2 from the S, 4 from the P. So I'm going to write down the symbol for oxygen, O, and then I'm going to put my electrons in. Now, it's really helpful if we put our electrons in only 1 on a side before we begin to double up. So imagine this box, 4 sides on oxygen. I'm going to put 1 on one side, another one on another side, third side, fourth side, and that gives me 4 electrons. Now I have to start doubling up. So I'll go here, and I'll go here. So there's my Lewis symbol for oxygen. 6 electrons arranged around the oxygen symbol. Here's selenium. Highest shell in selenium is 4, and it's the same story. It's 6. So I'm going to put a symbol for selenium, 1 on each side, and then double up to get the 6. Now, if you recall, oxygen looked like this. These are in the same group. All elements in the same group are going to have the same dot structure. You can use Lewis symbols to predict what kind of ionic bonding is going to occur for main group elements. Now, what are main group elements? Well, think about a periodic table. You got the first 2 columns, you got the last 6 columns, and then you have the transition metals. Not transition metals. That's main group. That's main group. Here's an example. Calcium and chlorine. Calcium is in group 2. Group 2s are always going to end in S2. So that means the highest energy level is always going to have 2 valence electrons in it. So that means 2 dots. In fact, this is a rule that's really easy to follow. For main groups, whatever the column number is, that's how many dots you have. So back to our periodic table. Column 1, 1 dot. Column 2, 2 dots. Skip the transition metals and go to boron's column. That's 3 dots. Carbons, nitrogens is 5. Oxygens is 6. Fluorine and the halogens are 7s, and then 8 for noble gases. So calcium in column 2 has 2 dots. Chlorine is a halogen, column 7, so that means 7 dots. So I fill up almost my 8 dots. So what's going to happen? Well, for stability, they want to be like noble gases. For calcium, the easiest thing for it to do is to give up an electron, because if it had no dots, well, it would be like its closest noble gas, which is argon. So I'll transfer a dot into chlorine. Chlorine wants to have 8, a full octet, because it can then be like argon as well. So calcium is going to lose one of its dots to chlorine, but it still has to get rid of another valence electron. So that means it's going to require a second chlorine atom to transfer that second valence electron into. Well, now what's happened to calcium is calcium has become a 2+ ion. And I've created 2 chlorides that are each 1-. So when I put these together, I'll have CaCl2. Of course, you know there are other ways to do this, like charge swap can very quickly give us the correct formula, but this is why. It's this quest for stability that these ions are on that causes them to form the ions that they do. Ionic bonding occurs between easily ionized atoms, which typically are going to be metals, and atoms that have a high electron affinity, which are typically going to be nonmetals. So when a nonmetal and a metal bond, it's usually an ionic bond that's formed. Next video is going to be about another form of bonding that takes place when ionic bonding just doesn't make any sense. For example, we know that oxygen forms an O2 molecule. Think about oxygen's Lewis symbol, which we have already seen today. If I have 2 of these things, which one's going to give up the electrons to become stable or gain electrons to become stable? Both of them want to gain electrons. So obviously, transfer of electrons out of this oxygen into the other one is not going to happen. There has to be another mechanism, and we'll discuss that in the next video.